Hello and welcome to the lecture for handout 2. Alright, so today we're going to talk about work and kinetic energy using some calculus concepts. This handout only has one topic, so once we talk about work and kinetic energy, we will be done. Okay, so our objective here is to recognize that work is force integrated over displacement, and discern the expression of kinetic energy can be derived from the definition of work. So we have a couple of calculus concepts we want to cover, namely the dot product, which is also called the scalar product because it is a form of vector multiplication that gives you the scalar, hence the name, and then the idea of substituting differentials as a solution method. So let's define the dot product to get started. So, big idea, there are two ways to multiply vectors. You either multiply vectors and get another vector, or you multiply vectors and get a scalar. We're obviously talking about the second way, called the dot product. We will talk about the other form of vector multiplication in a later handout. All right? So one way to multiply vectors gives a result that is a scalar. All right, that is called the dot product. Okay, the notation, the actual operator is a dot, hence the name. And in this case, I'm taking the magnitude of the multiplication of the dot product. Now, it's not the it's never going to be a vector. So here, really, what I'm saying is I'm taking the absolute value. Okay, and so then I'm going to have AB times cosine of theta. All right, so that's the notation. The dot is the dot product. It's like the typical multiplication symbol, and it's giving you a scalar, just like the typical multiplication symbol for that matter. But it is definitely a separate operator because it is between vectors. Whereas if you've seen a dot representing multiplication between scalars, you know what to do. But regardless, so there's the dot product, and it's going to be equal to the magnitude of A multiplied by the magnitude of B times cosine of the angle between the two. All right. So this is just showing that A is in fact the magnitude. For a two-dimensional vector that just has an x component and a y component, we'd find it by using the Pythagorean theorem. All right, and then you do the same thing for B, and then theta is just the angle between the two. Another way, besides denoting the magnitude of the dot product like this, is to write it, again, it's going to be a scalar, but it's just the sum of the products of components. So the dot product of A and B would be AX BX, or AX times BX, plus AY times BY. So we're just multiplying together the matching components. Multiply together the x components, multiply together the y components of the two vectors, and then take the sum of each of those products. Okay? In physics, work is the dot product of force and displacement. So work is really kind of the example that we're going to see of a real-life application of the dot product. Here's an example of a couple of vectors, A and B. If they had an angle between them of theta, then we could find the magnitude of their dot product, essentially multiplying those two vectors together. Taking this approach, that would be fine. We could just find each of their magnitudes and then multiply it by cosine of the angle between them, which is shown here in the figure as theta. Or we could take this approach. Either way would get us there. Okay? And that would give us the product of those vectors. Okay. So that's the dot product. We're going to see it in practice in our examples. But we have another concept that's related more to the background physical ideas that we're presenting, because of course we are talking about work here. So let's define this other calculus concept and then show where it shows up, which is going to be in the key formulas below. Okay? So what is substituting differentials? Well, first of all, what is a differential? Well, a differential is the part of an integral or derivative that has the form d of some variable. Okay? So we've seen it before. For example, we saw that velocity was dx over dt. All right, so that would have been the differential of position and the differential of time, so dx and dt. Right. For another example, an integral from 0 to 5 of x dx has the differential dx. Okay, so that's the term. Sometimes differentials need to be substituted in order to solve an integral, because perhaps your function isn't matching up with your differential, but there's a way to make it match up. Okay, and we're going to see the derivation below as a great example of that, what that means, because it's kind of an abstract idea. Okay, so first of all, let's define work and get back to the dot product idea. Okay, so here we have the definition of work. Okay, so W for work, it is the integral of the dot product of f and dx. Okay, so essentially what this tells us, how we read this equation, is we're integrating all of the components of f that are parallel to the displacement x. Why parallel? Well, look at the definition. When I take cosine of an angle between two vectors, if the angle between the two vectors is 90 degrees, if that's theta, what's cosine of 90? It's 0, right? Or if the two vectors are parallel, right? If my b vector was, say, parallel to my a vector, well, in that case, the angle between the two would be 0 degrees. What's cosine of 0? 1. So what that's telling us is that the dot product gives you full magnitude, maximum magnitude, when the angle between the two vectors is 0. So if your two vectors are parallel, then the dot product is just the simple product of the two, okay? So that's why I'm saying that we're integrating all of the components of f that are parallel to dx, okay? All right. So work is the integral of the dot product of force and displacement, all right? So now you could rewrite the dot product as just f dx cosine of the angle between the two, okay? Now, if that angle is constantly changing, then that's a special kind of integral that's beyond the scope of the class. But if that angle was constant, then it would just come out of the integral, okay? But does f just come out of the integral? Well, not necessarily. That's one of the key ideas here, is this is always the case for work. So we can apply this to any type of work, and I'll show how it applies to a work done by a spring that we've seen before. But it also applies to work done by a force that is varying. And I guess for the spring, it actually is in fact varying, but it's still it's a result that we've seen. It's an equation we've been given before. Okay, we're going to see where it comes from calculus. But we could think of a force that is not varying with x, like gravitational force, for example. Right, in that case, the gravitational force is just mg, which means it would just come right out of the integral, and then we'd simply have, so in that case, we just have mg, and then 0 to x dx, which in this case is just you'd be multiplying by delta x. So then just be mg times delta x, okay? And then, of course, cosine of the angle between the two if they're not parallel. All right, so that would be a case of a constant force. But we're now, due to this general definition of work, able to deal with forces that are not a function of x. So when I say but force is a function of x, that would be true for forces that match up the title of this handout, varying forces. All right, because those are, in fact, all the forces we're going to look at. All the examples cover varying forces. Okay. So last idea that I want to cover, because it's something you've seen before, and I want to back it up with some calculus concepts, is the work kinetic energy theorem. Right? There it is, also known as the work energy principle. It's kind of two names for the same thing. And if you recall, it says that the work is just equal to the change in kinetic energy. Okay? So simple idea, very powerful, very much consistent with a conservation of energy approach to solving problems. All right? Now, where does it come from? Right? Where do we get this? Because we can just be given it, say that it's valid, say that it makes sense, units match up, that's great. But how do we actually derive it? Well, let's derive it using calculus, okay? So we're going to start with the definition of work. I'm just going to rewrite this a bit. So I'm going to rewrite the dot product as the component of f that is parallel to x, okay? And so that's all I've done is just say, okay, well, f dx cosine theta is the same as just f cosine theta dx. F cosine theta is just f parallel, okay? Because that's the parallel component, okay? Again, because it's cosine, all right? Okay, and then I'm evaluating it from 0 to x, excellent, okay? And so then we're going to replace f with ma, okay? Why? Well, because of Newton's second law, okay? We can absolutely do that. That's true. Force is always mass times acceleration. Okay, so now I have this integral 0 to x, mass times acceleration dx. So does the ma just come right out of the integral? No, because acceleration certainly can be a function of x, right? Okay, so let's rewrite acceleration as its derivative definition of dv over dt, all right? Because it is, after all, just the first time derivative of velocity. Okay, still good, except now we have a bunch of differentials and no obvious way of solving the integral, right? Well, now we do the substitution, okay? So what I'm going to do is I'm going to say, okay, well, I have dv here, and I have dx over dt, okay? Because the dx is in the numerator, the dt is in the denominator. Okay, so now we're going to express dx over dt as v, because after all, that's the definition of velocity in the same way that dv over dt was the definition of acceleration. Okay, and then we're going to integrate over dv. We're going to leave that as our differential instead of dx. Okay, see what we've done? We've done a differential substitution. Okay, so here we go. Look what we did. I rewrote dx over dt as v. Okay, so that was that. And then I just left the dv. And here I've matched up the colors. Okay, so then this circled thing in green is the same circle in green, and the purple circle is just the dv. Notice my limits of integration have changed from 0 to x to 0 to v. because of that differential change, because now I'm differentiating over velocity. Okay, so now we're going to go ahead and evaluate that integral. I always set my lower limit as 0. I'll comment out at the very end. And so when I go ahead and evaluate that, just using the fact that this is just a first order polynomial, then the v to the first power becomes v squared, and I divide by 1 by 2. Right? So it's a 1/2. All right, and then evaluate 0 to v, and there we go, 1/2 mv squared. Okay, that's my change in kinetic energy, and it's for a initial kinetic energy of 0, which is to say a v initial of 0. Okay. And that was, we could have done it differently, but we just kept it that way. So we assumed that that velocity at x equals 0. So we're saying that v naught at x equals 0 is 0. Okay, and it's totally valid if we have some non-zero initial velocity, but this works. Okay, all right. So there you go. You can see kind of how we can use this approach of integration to show where theorems that we've been given before come from. Okay. Well, let's move on to the examples, finally, right? Okay. So 2 examples today, both about the topic of varying work, okay? One is a 1D problem, and then the second one is a 3-dimensional problem. Okay, so first our 1D problem. A spring that obeys Hooke's law has a spring constant of 945 newtons per meter. How much elastic potential energy is stored in the spring if it is stretched 13.3 centimeters? And you might think to yourself, oh, I know, this is a formula for this. I use 1/2 kx squared. And that's true, but let's rederive that formula, or let's derive it, show where it comes from, which is not particularly hard using our integral definition of work, and then actually plug in the numbers. Okay? So first we're going to use the fact that a change in potential energy is equal to the negative of the work done by the spring. Okay? This is true of any work that creates a potential energy. That just happens to be a work done by a spring. This would hold true for work done by gravity as well. All right? So that means if I solve for the work done by the spring, it's going to be equal to negative kx. Okay? And this is just the force from Hooke's law. It's negative because it's a restoring force. It's in the opposite direction of the displacement, so the negative is important, okay? And so all I've done here is just set that up. You could also think of the fact that this is f of the spring times dx times cosine of the angle between the two, and in this case, the angle between the two is 180 degrees, and that's where the negative comes from, okay? But either way, there we go. We've got our expression inside the integral. We're going to be evaluating from 0 to x, or in other words, from equilibrium at 0 to x final at 13.3 centimeters, or 0.133 meters. All right. We'll then go ahead and actually do the derivative, or do the rules of antiderivatives, and then it just becomes a 1/2 kx squared. See, from doing the integration. All right. Then evaluate it from 0 to x, and there we go. Then what we find then is our work done by the spring is equal to the negative of the change in potential energy, and there we go. That's our potential energy of a spring that we've seen before. And this is where it comes from. Now we can plug in the numbers as promised, okay? And right, it's just stating what I said. And so then when we go ahead and plug in, so we're asked to find, in this case, the change in potential energy. All right, so that's going to be a positive value because this is going to be the negative of the negative work done by the spring. And that makes sense because, of course, the spring is storing energy, so there's a positive change in potential energy. So then 1/2 times k times the displacement of the spring squared. All right, and that gives us 8.36 joules. Excellent, okay? Now again, this is an easy formula to kind of have at hand, and it applies to any Hookean spring. That's the spring that obeys Hooke's law. But what about springs or elastic materials that don't? Well, then you have to integrate it, because then you can be given any force function. And that's what I have in part B. So now the spring is replaced by a rubber band that is non-Hookean, so it does not obey Hooke's law. We can't just plug in kx into the integral, or negative kx for that matter. All right, it has a restoring force that is dependent on extension with this function, okay? So it's still a polynomial, but we have a lot of roots that are fractions, so that they represent some more maybe complex fitting function. Maybe this is based on some empirical data, right? Maybe someone did some observations and then used a best fit, and this was the function they came up with. Also notice that not all of the values are negative. We have positive values as well. So essentially we have, so this is the restoring force of the spring has a negative term, but then it's got 2 positive terms. Those are meant to represent the rubber band failing. Because unlike a spring, a rubber band is more prone to permanent deformation. It's going to start ripping and permanently getting deformed. And so that's the idea, is that the spring this rubber band is starting to give out, and that's what these 2 terms represent. Okay? I give you the values of each of the terms, the numerical values, and the correct units on each of them. All right? So we have 250 for alpha. That's the coefficient attached to this this term that's raised to the 7/3 power. The beta is raised to the, is times x to the 4/3 power, and beta is 805. And then that's newtons per meter to the 4/7 power, and so on. And then finally, gamma is a larger one at 1210. Okay? All right, so then the question is, how much work does the rubber band do if it is stretched 13.3 centimeters? Here I'm not asking for the stored potential energy. If I was, it would just be the negative of the answer that we're going to get. And do note that, because in part A I asked for the stored potential energy. Here I'm asking for the work done by the rubber band. Okay, so let's go ahead and find out how much work the rubber band did. Okay, so let's go ahead and then solve for the work done by the, I still have S here, but think rubber band. All right, I plug in the function, all right, and it's going to be the negative of that function, okay? So it's going to be the negative of the work done by this force, okay? Because it's opposing that force, okay? This is the force being done on the spring, and it's the negative of that force, okay? That's the way that the problem is written, okay? We're going to be evaluating from 0 to x, okay? And so all we then do is the antiderivative of each of these. They're a bit odd because they are all fractional exponents, but it's the same idea. You add 1 to the exponent, so 7/3 plus 1 is 10/3, and then I divide by 10/3, which is the same as multiplying by 3/10. Same thing here. 4/7 plus 1 is just 11/7, and then I divide by 11/7, which is multiplying by 7/11, okay? And this one's really straightforward. This gets raised to the 6th power, and then I divide by 6, okay? And then at this point, the alpha, beta, and gamma are just along for the ride. We'll plug in the numbers later. And then we're evaluating from equilibrium at 0 to the extension of 13.3 centimeters. Okay? And we'll distribute in our negative, and then we'll just have all of our values. So we have a positive term. So the work done by the spring is this term minus these two. Okay? And there we have it. So the work done by the spring is negative 21.4 joules. Okay? That's how much work it does. It makes sense that it's negative work because, after all, the spring is, it's being extended. It's trying to, I said spring, I mean rubber band. The rubber band is being extended. It's trying to return to its original length, so it's doing negative work. If you were the one pulling on the rubber band, you'd be doing positive work on the rubber band, but the rubber band is doing negative work while you do positive work. And if you're maintaining constant velocity, those two works would be equal. If you accelerated the rubber band, then maybe your work is greater. Okay, but here it doesn't matter. We're not interested in whether this is constant velocity or not. We're only interested in the work done by the rubber band. Okay, all right. So there we have it, the value. Okay, all right, excellent. And by the way, the stored potential energy in the rubber band would just be positive 21.4 joules. All right, and it's interesting. This must be a really stiff rubber band if it did more work than the spring, or maybe it's a really loose spring. Okay, all right. Let's move on to our last example. Okay, so this is the 3D one. So the idea here is we have a simpler function, all right, but it is just some arbitrary function. There's some force out somewhere in space that in the x direction has a cubic relationship on displacement. In the y direction, it increases linearly, and then in the z direction, it is decreasing in a quadratic manner. All right, so it's some sort of 3D force function out, and maybe caused by planets or gravity or whatever have you, or maybe some sort of electromagnetic phenomenon, but it's got I hat, j hat, and k hat notations. And remember, I, j, and k refer to x, y, and z respectively. Units are newtons, and I don't specify the exact values of the coefficients. We just know that they have the correct values for their overall force to be in newtons. Okay, and then we're told the particle has a mass of 1.26 kilograms, and we're asked how much work is done as the particle moves from this position to this one. All right, and then if nothing else changed except the initial z coordinate of the particle, then what would the z coordinate need to be in order for the force to do zero work? Okay, and in this case, we're actually not going to end up using the mass because I don't ask for any acceleration or anything, and so we're just going to find the work and then be done. Okay. All right, so let's go ahead and tackle part A. So here we have just our general definition of work. Okay, here it's good that we're denoting it as a vector because after all, with this, we have all these different components. And then so r, that's the displacement vector, we can think of as being split up into individual displacement vectors, dx, dy, and dz. Okay, all right, and that's really, we really think of dr being split up into those individual pieces. Okay, and then I'm going to then think of the work integral then as just being the dot product of each of the components of the force vector with the appropriate differential. And note that in each case, the angle between the force component and the differential vector is 0, because cosine of theta, or I should say the angle is 0 degrees, because cosine of theta is 1. Right? That's why each of them is just doesn't have any other angle tacked onto it, or cosine of an angle tacked onto it, which would be a value between 0 and 1. Instead, it's just fx dx, fy dy, and so on. Okay, so now we'll just plug in our function. So all I'm doing here is, zoom in a bit on it, is plug in the function for x. That is then going to be multiplied by the differential, or rather actually integrated over dx from 4 to 7, right? Because we started at 4 and we want to finish at 7. For the y case, we're starting at 0 and we're finishing at 13. So the limits are from 0 to 13. There's our function in the y. And then in z, we have our function, okay? And this one is negative. Let's see, I think it shows up as negative in the next line. So there's a typo there. All right, but I'll fix it on the upload. All right, so we have 3.5 times z squared. Okay, and then we're going to go ahead and then write out our terms here. This is just, here I've just done the rules of antiderivatives, right? That's always the first step before I evaluate the limits. Here we have to definitely be careful to evaluate the limits because we do have non-zero lower limits on 2 of them. Okay, so let's go ahead, next step. So here I finally have the correct sign. So this should have been negative, should have been negative. Here is the correct negative, which means the final answer is correct. Okay. Let's see. All right, so I pulled the 2/5 out in front, and then I evaluated the upper limit of 7. I raised it to the 4th power, so that's why I have 7 to the 4th minus 4 to the 4th. The y squared is just 13 squared because 0 squared is 0. As far as the last term, the z term, pull the 7/6 out in front, and then 9 cubed minus negative 5 cubed. An interesting thing about a cubic is since negative 5 cubed is a negative, but we're subtracting the lower limit, this entire expression in the parentheses is a positive value. So the bigger that, if this was a larger negative number, then this z term would be doing more negative work, okay? All right, and that will come up in part B. So here's the total amount of work done by this force over this particular displacement, okay? And it's 30.7 joules. All right, if we'd moved in any different final position of x, y, and z, we would have had a different number here, okay? But notice how we can just split it up over those different components, okay? All right. Now finally in part B, I ask, if nothing else was changed except the initial z coordinate of the particle, what would the z coordinate need to be in order for the force to do 0 work? Okay, so the whole idea here is that I have all the same terms. The only thing is I've replaced my negative 5 with a variable z naught. Okay, and I'm going to set it equal to 0 joules instead of the value I found because I want it to equal 0 joules, and I'm going to solve for z naught. And it's as simple as that. Okay, I don't have to go back to the integral. I can just go back to that final step. All right, so here I've just found that this term here is 858 joules. The 13 squared is, of course, 169. And then I'm going to take the negative 7.6 times 9 cubed, which is negative 851, and then I'll move this term over here. And so what we have is we've got a negative times a negative when I distribute the negative n, so then it becomes positive, but then when I subtract it from both sides of the equation to bring it over to the right side, it becomes negative. Okay, so that's important. And then when I take 858 plus 169 minus 851, I'm left with 177 joules. All right, and then I've got my negative 7.6. So again, I have a negative here. I use losing signs now and then. All right, but here I pick it up again. All right, so then I'm going to multiply both sides by negative 6 over 7, which is what that is, and then times 177 because I just cross multiplied. All right, and then I'll just take the cube root of both sides in order to isolate z naught, and I should get a negative value. And here I do, and it's just slightly greater in magnitude than it was before. So the idea is I just need to have z start a little bit sooner than negative 5, negative 5.33, and then I'll have no energy at all. Right? And at that point, the total work done by the forces as moving through space would be 0. Okay? All right. So as far as the homework, there's going to be 2 problems very similar to the examples I did. We've got a non-Hookean spring, and then we've got a force in 3 dimensions and some similar questions. Okay? All right. Well, thank you so much for watching this lecture for handout 2. I hope it's been interesting and informative.